Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder if those interesting research findings you read about are actually true, or just a fluke? Today we're diving into a super important topic in science called p-hacking, and how different ways of thinking about research can handle it. Imagine researchers doing a bunch of tests and then only telling us about the ones that look exciting. Does that mess with the results? Let's unpack this. So, what exactly is p-hacking? Think of it like this. You are looking for a specific result, maybe something that proves your idea is right. You run a bunch of different tests, like little experiments, and most of them don't show anything interesting, but one or two do show something cool. P-hacking is when you only report those cool results and pretend like you only did those few tests, without telling anyone about all the other tests that didn't work out. It's like finding a needle in a haystack and then only showing the needle without mentioning the whole haystack you dug through. This is a big deal because it makes it seem like scientific findings are stronger than they really are. It is considered a questionable research practice and can lead to a lot of misleading information out there in science. Now, the really interesting part of this research is that it looks at this p-hacking problem through the lens of two different ways. Scientists think about testing their ideas. One is called the error statistical approach, and the other is the formal inference approach. The core idea here is that p-hacking might mess things up in one of these approaches, but not the other. Let's break down what happens in this error statistical approach. Here, scientists are really focused on the overall process, including all the tests that were done, even the ones that weren't reported. They look at something called the actual family-wise error rate. This is basically the chance of making a mistake across all the tests you ran. If you run two tests at a 5% significance level, the real chance of getting a false positive across both isn't just 5%, it's closer to 10%. When you p-hack, you are hiding tests, and this actual error rate creeps up, making your reported significant findings less reliable. It is like trying to catch a rare bird if you look in 100 different places without telling anyone, and finally find it. The odds of you finding it by pure chance are much higher than if you only looked in one spot. But here is where it gets fascinating. In the formal inference approach, things are different. This approach focuses only on the tests that are actually reported and formally put out there. If you only report one or two specific tests, then only those tests matter for the formal inference. The ones you didn't report, the ones you p-hacked, are essentially ignored in this view. The logic is that the actual error rate from all your secret tests doesn't apply to the specific, formally presented inference. It is like saying if you auditioned for 10 singing competitions and only the one you won gets reported, the fact that you might have fluked your way into winning doesn't invalidate the win itself for the official record books. If the judges only looked at the final performance. The formal inference approach has specific rules for figuring out the real chance of error. They really drill down into what is formally stated and what is being inferred. One key idea is that type I error rates, that is the chance of a false positive, are only supposed to account for random chances in the data. They aren't meant to cover mistakes from bad study design, flawed measurements, or errors in how the data was collected or analyzed. Those are called systematic errors, and they're a whole other problem. Another principle is that the error rate for one test is separate from another. You can't just say one test's error rate is inflated because another test has a different error rate. They're like apples and oranges. You can compare their sizes, but you can't say one is an inflated version of the other. This one is crucial. A family-wise error rate is about the whole group of tests. It doesn't mean you can draw conclusions about each individual test within that group. It is like knowing the chance of winning any prize in a lottery doesn't tell you the exact chances of winning a specific prize. This is the heart of the formal inference approach. What matters is what you declare you are testing and inferring, not all the hidden steps you might have taken. If you formally report an inference about hypothesis X, that is what determines the error rate, regardless of other hypotheses you might have explored and then discarded. So, to bring it back to our main question, the researchers here are arguing that p-hacking, that sneaky practice of only reporting good results, really does mess with the error rates in the error statistical way of thinking. But in the formal inference way of thinking, where you focus only on what is officially reported, hacking doesn't actually inflate the error rates for those specific reported findings. Let's look at an example. Imagine a researcher tests their idea and gets a result that is almost significant, say a p-value of 0.061. Then they do something a bit sneaky, like removing an outlier or changing their analysis slightly. Now they run the test again and get a significant result, p 0.032. They report the second significant result, but they don't mention the first non-significant one. From the error statistical viewpoint, this is a clear case of p-hacking. They did 2 tests, and the actual chance of getting a significant result by luck, considering both tests, is higher than the 0.05 they might claim for the second test alone. But from the formal inference perspective, if the researcher only reports the second test and its result as an inference about that specific hypothesis, then that is what counts. The first hidden test becomes irrelevant to the formal inference being made. The error rate for that reported test remains at its nominal level, like 0.032 or 0.05, if that was the threshold. The key here is that the actual overall error from all the tests doesn't apply to that single formally reported inference. It is like saying the chance of you guessing heads multiple times in a row doesn't affect the truthfulness of your single flip result being heads, if that is the only result you declare. The author emphasizes that in the error statistical approach, you need to consider all the possibilities to truly understand how well tested a claim is. But from the formal inference side, that is like a fallacy of division, you are applying an overall probability to an individual event where it doesn't quite fit. The paper highlights that a researcher could formally report a more complex inference that does account for multiple tests, like saying there was a significant effect in at least one of the conditions. In that case, the error rate would indeed be higher. But usually, when researchers p-hack, they don't report that kind of broad inference, they pick out one specific significant result. A real challenge is that when you p-hack, you are often not just doing a few tests, but potentially an unknown number of them. This makes it nearly impossible to even calculate that actual family-wise error rate, which is a problem for the error statistical approach. The formal inference approach, by focusing only on reported tests, sidesteps this unknown number of tests issue. Interestingly, the two approaches aren't in total disagreement. They both agree that science is about different philosophies. They also both nod to the idea that the logic of the math might say one thing, even if the researcher has biases. The main disagreement is about where to draw the line between just exploring ideas and making a formal scientific claim. The error statistical approach sees the whole process, including the exploration, as part of the justification. The formal inference approach, following thinkers like Popper, says that the how of discovering an idea is separate from the how you test, and justify it once it is formally presented. The error statistical approach has a minimal severity requirement, meaning you need to check your assumptions thoroughly to make sure your findings are robust and not due to errors. They see p-hacking as violating this. The formal inference approach, on the other hand, says that the nominal error rate is valid under a specific ideal scenario where all assumptions are met. It is like saying a formula for speed is distance over time. That formula is correct even if your speedometer is broken. The broken speedometer is a separate issue, a systematic error that impacts your real world measurement, but not the validity of the formula itself. They use the Texas sharpshooter fallacy as an example. This is where someone shoots at a wall, then paints targets around the bullet holes, claiming they're a great shot. The error statistical approach would say this is bad because you are not ruling out the fraudulent behavior. The formal inference approach would say, okay, the shooting itself might be flawed, but if you formally report this specific target as your objective, the probability of hitting that specific target by chance is still calculable, even if the whole setup is dishonest. The statistical inference is about the probability, not the honesty of the process. The paper also touches on hiding null results, those tests that didn't show anything significant. In the error statistical view, hiding these is part of the p-hacking problem. In the formal inference view, it might not inflate type I error rates, but it could still be a problem if those null results provide important evidence that is being hidden. If you test 20 colors of jelly beans and only green causes acne, reporting only green and ignoring the other 19 non-significant tests might bias the overall claim about jelly beans and acne. So, to wrap up this really interesting distinction, p-hacking is a problem, but its impact on type I error rates depends on how you look at statistical testing. In the error statistical view, p-hacking messes with the actual error rate because it includes all the hidden tests. But in the formal inference view, if you only report a subset of tests, the error rate for those reported tests remains valid, unaffected by the unreported ones, because they are simply not part of the formally declared experiment. This all has some big implications. It suggests that when we talk about p-hacking, it is important to be clear about which philosophical approach to statistics we're using. It also means that some common solutions to p-hacking, like pre-registration, might be more focused on the error statistical approach without fully accounting for the formal inference perspective. The author argues that researchers need to be clearer about their assumptions when discussing p-hacking. For demonstrations of p-hacking, they often use the error statistical approach, which might paint a more dire picture than the formal inference approach would suggest for reported findings. When it comes to the big issue of the replication crisis, why studies often fail to be reproduced, the error statistical view suggests inflated error rates from p-hacking are a major culprit. But the formal inference approach suggests that while type I errors happen, the rate is as expected, and that perhaps other more subtle issues, like unknown unknowns or unrecognized interpretational errors, might be the real reason for replication failures. This research really makes you think about how we interpret scientific claims. The formal inference approach, with its focus on what is explicitly stated and tested, offers a different perspective. It suggests that while p-hacking is still a questionable practice, especially ethically, its statistical impact on the formally reported findings might be less severe than often assumed. It highlights that the validity of a statistical test is tied to the terms under which it is officially presented. However, I think it is crucial to remember that the actual process of research does matter for building reliable knowledge. Even if the formal inference approach allows for valid statistical inferences from reported findings, the hidden exploration and data dredging can still lead us astray in the broader scientific conversation. It's like the difference between a magician performing a trick by showing you only the final flourish versus you seeing all the sleight of hand that made it happen. Seeing the sleight of hand might not invalidate the trick in the eyes of someone only looking at the final outcome, but it tells you something important about the nature of what you just witnessed. So, the big question is, should we focus on the technically correct formal inference of reported results or the more holistic view of the entire research process, including all the hidden steps? This paper leans towards the latter for actual scientific progress and trustworthiness. What do you all think? Does p-hacking invalidate findings in your eyes, or is it more about the formal reporting? Let me know in the comments below. And if you found this breakdown helpful, please give this video a like, subscribe to RUBIN'S Mind Lab for more science explorations, and hit that notification bell so you don't miss our next dive into the mind. Thanks for watching, and I'll see you in the next one.